going to be looking at experimentally determining rate laws from initial rate data. And we'll start with a simple example where we're just tracking one compound. What we're looking at here is the reaction that goes on right here, and we're looking at the initial rate of product being formed. It doesn't matter which one we're looking at because the stoichiometry is 1-to-1. These are the experiments that are being carried out. These are the initial concentrations of the reactant. We have a rate law where we're looking to find K, that's the rate constant, and we also want to find the value of N, the exponent that has to do with the reactant. And we have our initial rate data here. So we're going to find N first. And the way that we're going to do this is we're going to look at two different experiments. And let's take a look at these two right here. We know that we can look at rate 1 and compare it to rate 2. Rate 1 is going to equal K times the concentration of our reactant raised to some power, N. And N is what we're trying to find out. The rate constant stays constant. It's constant. So rate 2 is also going to be proportional, or going to be equal, to the concentration raised to some power. So now let's rewrite these as actual rates. And you always want to start with the larger rate on top. It makes it easier to see what's going on. So we're going to start with 0.081 equals K. And we're going to use the concentration that matches up here. So it's 0.20 to the N power. And then we're going to take this rate, and it's 0.020 equals K. And this time it's to the 0.10 raised to the N power. Well, let's start canceling stuff out. Well, 0.081 divided by 0.020 is essentially 4. So 4 equals, and then the k's cancel because they're constants. And 0.2 divided by 0.1 is 2. So what we have is that 4 equals 2 to the N. Therefore, N has to equal 2. Now we're going to figure out K, including units, by picking any experiment and plugging into the rate law. So we established that N equals 2. So our rate law is rate equals K times the concentration of our reactant squared. So we're going to solve for K by pulling any one of these out. And so let's pull this one out here. We're going to have 0.020. And I'm going to redo these units here. Instead of moles per liter, I'm going to use it molarity because it's a little easier when we get to the end to use that. So 0.020 molarity to second to the negative 1 equals K. And then we're going to have this concentration squared, so it's 0.10, and this concentration is in molarity squared. So when we solve for K, we're going to see that K equals 2.0, and it's going to be molarity squared negative 1. And then we're going to have to cancel these out too. So we have molarity squared. When we do that, we get K equals 2.0. That one cancels, the square goes, and we have molarity to the negative 1 seconds to the negative 1. So there is our value of K. Now we can rewrite molarity as moles per liter, much as they did here. So if we've inverted moles per liter, this becomes liters over moles, so it's liters mole -1, seconds -1. So either one of these is correct in terms of the units. So our final rate equation is rate equals 2.0 mole -1 second -1 times the concentration of our reactant squared. Notice that the units of K depend on the overall reaction order. So this is a second order reaction. If it was third order, then we would have molarity squared here. If it was fourth order, it would be molarity raised to the fourth power, and so our values of K would shift. Once we have this rate law, then we can solve for any concentrations of the reactant. So in this case, we have the reactant at a value of 0.25 molars, so we simply plug in the equation. We have rate equals, and our value for K is 2.0, molarity -1, second -1, times 0.25 squared. And your answer ends up being 0.125, and it's moles, liters -1, seconds -1.